Thank you, and welcome again for the continuation of the topic we had started, the quantity of heat. So we started by defining a few terms as we introduce ourselves to this topic, and so far we've covered quantity of heat, the heat capacity, specific heat capacity, determining specific heat capacities of different materials. We also studied now change in state or change of state where we have now. We have seen the latent heat of fusion, which is the heat energy absorbed or released as a solid changes to a liquid or a liquid changes to a solid respectively. And now we are looking at latent heat of vaporization, which is the amount of heat energy given out as a liquid turns to a gas or to a vapor. So when a liquid is turning to a vapor, the temperature of the substance remains constant, and as it is constant now, some heat is being absorbed to change the structure of the liquid into a gas. Such heat, which is absorbed at a constant temperature, is what we are referring to as the latent heat of vaporization. After latent heat of vaporization is absorbed, then the substance starts now increasing in temperature. And we have earlier on discussed the method of mixtures whereby we are checking the steam which will be condensed when channeled into a calorimeter with cold water, whereby the steam now will lose water and condense to become water. But in this method, or in this topic now, we will be checking the same thing, latent heat of vaporization, but now using the electrical method. So under the electrical method, this is what we do. The necessary apparatus are arranged as follows in the experiment to determine latent heat of vaporization. You see that we got the system arranged in this. We have the system organized in this manner. We have a rheostat here which controls the current so that it remains a constant. That a constant value of the current being supplied is maintained. So that's why we have a rheostat there. A rheostat. Now we connect this one to an electric heater. So the heater coil is here. The heater coil is here. Then we have a voltmeter across here. Voltmeter across there. So here now we got a flask which is having water. We have a conical flask here containing water. Then we have a delivery tube, and along the delivery tube, which is not transferring steam, we have the delivery tube taking water into a beaker. So water droplets will be condensed and collected. So this is a beaker. So we have this system to enhance the cooling. The cooling was the steam generated. So we have cold water which enters here, and and after the water has been warmed, as it cools, the steam it exits. So this is warm water out and cold water in here. Cold water in through there. So we have a beaker here. And what we have here is water where the electric heater has been dipped. This heating coil has been dipped here. This is water. This is the heater. The heater coil gets dipped like that. So now, in this experiment, we can now check the procedure, necessary procedure for the necessary results. Okay, so you set the apparatus like that, and once the apparatus has been set like that now, the first thing we should know is measure the mass of the empty beaker, and you place it below this delivery tube. But before then, you can switch on the current, until, and wait until, then you wait until, water flows out or issues out at a constant rate. Then place an empty beaker of mass M1 below the delivery tube. And immediately start timing. And immediately you start timing. So after a suitable amount of water as collected in the beaker, withdraw the beaker, yeah, as you stop timing. Then after that, you can now record the time t and that's a mass of the beaker with the water, mass 2. Beaker with the water, mass 2. Therefore, I'm now saying, remember, we are using a rheostat to adjust the current so that you may ensure it is constant. Therefore, you should also have recorded, before stopping, you should have recorded the voltage reading and the current reading. They are very important. Therefore, now to analyze the results, we say that voltage is equal to V and current is equal to I, the current which was being supplied in time t seconds. Then we can say of condensed steam will be mass of the beaker with the water minus mass of beaker alone initially. So the beaker is initially having mass M1, and now once you've supplied current here, water has been heated, generated steam, and the steam condensed in this system here, and after it has been condensed, it's collected here. Therefore now, we are checking the mass of the water which has condensed here. And we are saying it will be mass of the beaker when it was empty, subtracted from now when it is having water. So M2 minus M1. M2 minus M1. Then after that, now we will see. Assuming that no heat loss to the surrounding, heat supplied by the heater will be equal to heat absorbed, or the heat, the heat, because it is the heat which has been gained by the steam, so the steam will lose it. So the heat supplied will be heat absorbed by steam to evaporate. So the heat supplied by the connection here will be the same heat absorbed by this water, so that it vaporizes. By water, so that it becomes steam. So water, so that it may become steam, it absorbs the heat which has been supplied by the current. Okay. VIT will be equal to heat absorbed by water, so that it vaporizes. Because at vaporization point, there will be no change in temperature. Then the heat absorbed at that point will be mass times the latent heat of vaporization. The mass which are given, or the heat which are given mass of a liquid absorbs, so that it will become a gas. So it happens at a constant temperature. Therefore, latent heat of vaporization will be given by VIT divided by the mass. So that is the simple demonstration of how the latent heat of vaporization of a given liquid can be determined using the electrical method. So with that, we can now have an example. I think the example we'll have here is general. It will involve several heat absorptions, and we'll see how to go about it. How to go about it. So the question says, calculate the quantity of heat. Calculate the quantity of heat required to change 0.5 kilograms of ice from negative 10 degrees Celsius completely to steam at 100 degrees Celsius. Take specific heat capacity of ice. Specific heat capacity of ice is 2100. Then we thought specific heat capacity of water is 4200. Then again, a specific latent heat of fusion latent heat of fusion of ice is 3.36 times 10 to the power of 5. Then specific latent heat of vaporization of steam, latent heat of vaporization of steam is 2.26 times 10 power 6. Yeah, so these are the constants given. These are the constants given. So we are told to calculate now the amount of heat energy required for this process to occur. Ice at -10. Ice at -10 degrees Celsius to change steam at to steam at 100 degrees Celsius. Change to steam at 100 degrees Celsius. So let's now analyze the question well. Solution. Calculate the quantity of heat required to change 0.5 kilograms of ice from -10 degrees Celsius completely to steam at. So total energy, heat energy required in this whole process will be the heat required to change ice to 0 degrees Celsius, to improve or to increase in energy from -10 to 0 degrees Celsius. Then heat to change ice. So now the latent heat of fusion now. Latent heat of fusion to change ice of ice. To change ice from ice at 0 degrees Celsius to water at 0 degrees Celsius. Then after that, now the heat required by water to change the water now, because at here it will, at this point it will melt to water. So after melting to water now, the water now will gain heat until it raise water to 100 degrees Celsius. Then after that now, the water, when it is at 100 degrees, it now vaporizes, and we require the latent heat of vaporization of water until it turns to steam, still at 100 degrees Celsius. Therefore, that is the whole process now. This mass changing from when it is ice and completely until it becomes steam. Therefore, it will be the ice, first of all, in temperature until 0, and when the temperature is constant now at 0, it absorbs another heat, latent heat now of fusion, until the ice completely becomes water. And now it has become water. The water now raises again up to 100, and when it is at 100 now, it gains another heat now, latent heat of fusion, latent heat of vaporization, until it completely becomes vapor or steam. Therefore, the total heat energy will be, to change ice from -10 to 0, we'll have 0.5 times specific heat capacity of ice 2100 times change in temperature will be 10, from -10 to 10, from -10 to 0, plus latent heat of fusion of ice. So the mass is 0.5 at constant temperature. Latent heat of fusion of water will be 36 times 10 power 5. Then plus the water now, which is still 0.5 kilograms, times the specific heat capacity of water, times it is changing from 0 to 100. Therefore, the change in temperature will be 100. Still plus, now when it has become water at 100, require latent heat of vaporization, so that it may become steam. So that it turns to steam. So 0.5 by 2100 times 10, this gives us 10,500 plus here 0.5 by 3.36 times a million, no, 100,000. 168,000 plus at this level 0.5 times 4200 times 100. This gives us 210,000 joules. Then plus lastly 0.5 times 2.26 times a million. This gives us 130,000. Therefore, the total heat required for all that process shall be 105,000 plus 168,000 plus 210,000 plus 1,130,123. So we get 1,518,500 joules, which can be expressed in standard form as 1.5185 times 10 raised to the power of 1, 2, 3, 4, 5, 6 joules. So this is the heat energy required for the whole process. That's how it had to be calculated. Allow me give other two questions which were tested in a given mock, and we will be good to go. Let me get the questions here. Can again clear the board so that we may have the question well written and the space to calculate when necessary. So in a certain mock exam, students had been taught to do the following question. It's a session 2 question. So this topic is very sensitive. Very sensitive. We have questions in session 2 carrying very good number of marks. What is meant by the terms specific latent heat of, what is meant, part A. What is meant by the term specific latent heat of fusion of a substance. Specific latent heat of fusion of a substance. Then part B, they were told water of mass 250 grams at a temperature of 65 degrees Celsius is put in a well-lagged copper calorimeter. Of mass 80 grams. So the calorimeter has a mass of 80 grams. So a piece of ice which is at 0 degrees Celsius and mass 10 grams is placed, and mass 10 grams is placed in the calorimeter and the mixture stirred. It's placed in the calorimeter and the mixture stirred. The mixture stirred until all the ice melts. The final temperature T of the mixture is then measured. The final temperature of the mixture is T, is recorded. The final temperature is then recorded. Determine Roman 1. So determine is general. Determine, then Roman 1. Heat absorbed by the melting ice heat absorbed by melting ice. Heat absorbed by the melting ice at 0 degrees Celsius. Heat absorbed by the melting ice. Then part B, the heat absorbed ice. Heat absorbed by the melted ice. Water, because it has now become water, and put in brackets water, to raise to temperature T. To raise to temperature T. Can you give your answer in terms of T? Roman 3, we told to determine the heat lost by the warm water and the calorimeter. Heat lost by the warm water, calorimeter, still in terms of T. In terms of T, the final temperature T of the mixture. The final temperature T of the mixture also has to be calculated. It also has to be calculated. Then we're told to take specific latent heat of fusion of ice. Latent heat of fusion of ice to be taken as 334,000. 334,000. Then next, specific heat capacity of water is 4200. Then specific heat capacity of copper, the copper calorimeter. Heat capacity of the calorimeter is 900. For water, we know it's 4200. It's been used several times. Yeah, so we can go into the solution for this one after reading the question closely. And first of all, we understand the processes involved. Here, we are having water inside a calorimeter. Mass of water and mass of calorimeter are given. Then now, when they are at 65 degrees Celsius now, ice is put there. It is already at 0. So it requires, first of all, heat of fusion, so that it becomes liquid water. Then when it has become liquid water, still at liquid water, still at 0 degrees Celsius, it has to raise to the common temperature T. To the common temperature T. And now, water and the calorimeter are losing heat to the ice. Therefore, we are told to find, okay, we have the definition first of all, latent heat of fusion, specific latent heat of fusion. This is the amount of heat energy required to change fusion, to change a unit mass of a substance from solid to liquid without change in temperatures or at constant temperature. So now we can move on to save time. Part B, Roman 1, the heat absorbed by the melting ice. So heat absorbed by melting ice will be the mass of the ice and latent heat of fusion, because there will be no change in temperature. Of the ice, whereby a piece of ice mass 10, so 10 grams over 1000, we can multiply it with the latent heat of fusion of ice. Latent heat of fusion of ice is 334,000, and this is giving us energy totaling to, the 3 zeros can cancel and we have 340 joules. So that is the energy required for that step. Then number 2, the heat absorbed by the melted ice. Therefore now it has melted. So melted ice, it has now become water. Therefore the heat absorbed now by the water now which has melted from the ice, it will be the same mass times specific heat capacity times change in temperature. So change in temperature from time T, from temperature T from 0. So temperature T minus it is from 0, it just remains T. Therefore, cancelling the 3 zeros, we'll have 42 T in terms of T, because T is a known in terms of T. Then Roman 3, we are determining the heat lost by the warm water and the calorimeter. So heat lost by warm water and calorimeter. To be by water, water is of mass 250 divided by 1000 times specific heat capacity times in temperature from 65 to this common temperature T. From 65 to this common temperature T. And now the copper calorimeter of mass 80. So of 1000 to make it as a. Okay, let me focus well so that you may see all the values. 80 times specific heat capacity, which is 900 for copper, times change in temperature still from 65 with the water until until temperature T, sorry. Therefore now we can make them in terms of T and we shall have 3 zeros cancelling, so 42 by 25. 1050 T. 1050 T. 1050 T, so it will be 1050 T. But here by 65 we will get 68,250 minus 1050 T. Then plus, for this side we shall have 3 zeros cancelling, therefore 8 by 9, 72. 72 by 65 give us, so first of all we'll have 4680. 10 minus 72 T. 72 T. Therefore we can group like terms here together and we shall have 68,250 plus 4680. This is giving us 72,930 minus 1050 and 72, we get 1122 T. 1122 T. Therefore, this is the heat lost by both water and calorimeter because they are together. Now, we are taught to find the final temperature T now to determine the value. So we'll say heat lost by water and the calorimeter will be the same as heat gained by ice as it melted plus heat gained by melted ice now, or water, by the melted ice. Therefore we shall have heat lost by water and calorimeter as 72,930 minus 1122 T, being equal to heat gained by ice to melt 340 plus heat gained by ice, the melted one now, to raise to the common temperature 42 T. Therefore we can group like terms together. The T's can come here so that they become positive. So when we had 42 to be 1164 T is equal to 72,930 minus 3340. This gives us 69,590. 69,590. Therefore, to get T, the final temperature, we divide with 1164. This gives us 59.79 degrees Celsius. So this is the final temperature which had been attained. So calorimeter and water have dropped from 65 to this temperature. Ice has melted first of all and then increased in temperature until it came to 59.79. So that is it. I can very fast bring another question to you very fast. So we can have another question still on the same because I will not again stand before you for the same topic. So we can have a question now to climax all these things. Another question now still involving the same. So first of all, write the question just as we have done in the former. First, start by copying down the question. We are told, so number 15, which says define the term specific latent heat of fusion, which is the term we just defined in the former question. So now we can go straight to part B, which is asking people, the figure below shows one method of measuring specific latent heat of fusion of ice. Then two funnels, A and B, contain crushed ice at 0 degrees Celsius. Therefore we got a funnel here so water is collected here once ice has melted. This crushed ice, and another funnel here. Another funnel, but in this one now, an immersed heater. This is an immersed heater. There is a heater for this case now, and again melted ice is being collected, but in this case now we have a bigger volume. Therefore in these two cases we have this as melted ice, beaker A and beaker B. Then in both cases this is crushed ice, melted ice. Then we told to do this. Then we are given here power for this one is 24 watts. The power is 24 watts. Then we told the mass of the ice from each funnel, the mass of melted ice from each funnel is measured after 11 seconds. 11 minutes, sorry. 11 minutes. Then the results are shown below. Mass of melted ice in A is given as 24 grams. Mass in B is given as 63 grams. What is the reason for the setup funnel? Part A. What is the reason for the setup? In A. Then determine the Roman 2. Determine the A. Determine the Part A, determine the quantity of heat supplied by heater of heat by heater. Then part B of the question, mass of ice melted by heater, mass of ice melted by heater. Then lastly, part C, the specific latent heat of fusion of ice. Specific latent heat of ice. Specific latent heat of ice. Latent heat of ice. Determine specific latent heat of ice. Therefore, now we can go now into the solution for this question very fast because of time. Let's see, our 40 minutes are over, so we are doing an overtime work here now. The part A of this question was defining a term, specific latent heat of fusion, and we said that is the amount of heat energy required to change a unit mass of a substance from solid to liquid at constant temperature. So that's what we call specific latent heat of fusion. Then now, in this setup, we are asked, what is the reason for setting up A? A is set up as, I think we had mentioned it is set up as a control experiment. A control experiment. So this control setup is to give us the amount of ice which could have melted naturally without the electric heater. So that now for B, where there is an electric heater now, we will count some of the melted ice to still have melted naturally, even without the heater. So, for the ice which has melted in B, to know the one which has really been caused by the electric heater, we will subtract the one in A, because the one in A is natural melting due to the environment heat, which could still have occurred in B without the immersed electric heater. Therefore, the reason of setup A is a control experiment to help us know the amount of ice which could still have melted due to the natural heat in the surrounding. Determine the quantity of heat supplied by the heater. Heat energy supplied by heater is equal to power times time. The power is 24 watts times 11 multiplied by 60 to make them seconds. So we shall have 24 by 11 by 60, 15,840 is the energy which will be, or the work done anyway, which will be released. Then Roman 2 part A, Roman 1, Roman 2 part A, we are determining the, okay, this is part A. Part B now, after determining the quantity of heat, we determine the mass melted by heater. So mass melted by heater will be 63 minus 24. Or in other words, we are saying in this setup, we are saying in this setup, if 24 could still have melted without heater, and the 63 has melted with heater, now it means there is that difference, which is strictly by the heater itself. So 63 minus 24 giving us 39 grams. 39 grams. Then we are told now specific latent heat of ice. So specific latent heat of ice, we usually say in the, when we were discussing the experiment, we say heat supplied by the heater is equal to heat used to melt the ice, and we call it latent heat of fusion. Latent heat of fusion. where we will have heat supplied by the heater calculated already, 15,840 joules, equal to the heat used to melt the ice. Because it is at constant temperature, it will be the mass of the ice, which is 39 grams. So we divide by 1,000 to make them as units, times the latent heat of fusion. The latent heat of fusion. So for latent heat of fusion will be, when we take 15,840, 1, 2, 3, multiply 1,000 divided by 39, and this should give us 15,840, 1, 2, 3, divided by 39. This is giving us 406, 153.8 joules per kilogram. Joules per kilogram. Joules per kilogram. So this is of energy, or 4.06 times 10 to the power of 5 joules per kilogram, written in standard form. So this is the specific latent heat of ice according to this experiment. So that's how these questions are approached. I believe at least you have gained something. So later on, during your free time, you can access KLB question, and I want students to go and revise now on their own, because any technical parts which required an explanation, I think I have done. Students can check the factors affecting melting and boiling points of substances, applications of the effects of pressure of ice. People can check melting, they can check boiling, people can check something called evaporation, effects of evaporation, factors affecting the rate of evaporation. You can also compare between boiling and evaporation. And lastly, you can check the applications of cooling by evaporation. Then after that, you'll be good to go. So thank you very much for finding time to follow us. May the Lord bless you. May the Lord keep you safe. I pray for your success. So thank you, students, for entrusting me. You can have a nice day. Thank you.